Hello, and welcome to this e-learning webinar from Shimadzu. I'm Andy Fernadel, a marketing manager focusing on the fuels, energy, and petrochemical sectors at Shimadzu Scientific Instruments. In this webinar, we will explore some of the more widely used LC-based methods for analysis of aromatic hydrocarbons in common fuels. Fuels are one of the more broadly used products made from crude oil and natural gas. Different types of fuels are specifically designed for proper performance in different types of engines. For example, diesel fuel, jet fuel, and gasoline all differ in terms of vapor pressures, ignition temperatures, hydrocarbon number, and hydrocarbon types, among myriad other characteristics. Additionally, various organizations establish regulations as to the chemistry of fuels. For example, the US EPA and FAA both have specifications for the chemistries of common fuels for motor vehicles and aircraft. The primary goals of these regulations are to limit the emission of harmful exhaust byproducts while also ensuring combustion efficiency. Aromatic hydrocarbons are naturally found in crude oil and make their way into fuel products during the refining process. In some cases, aromatics are added to the fuels intentionally, as they serve to boost the octane rating of the fuels, and they can also ensure the performance of elastomeric seals and gaskets within the engines. However, there are health and environmental concerns regarding the aromatic contents of fuels. Many aromatic hydrocarbons, such as benzene, are known carcinogens, and therefore it is advisable to minimize exposure to them. Additionally, aromatic hydrocarbons in fuels contribute to soot and particulates in the exhaust streams of burned fuels. For both health and environmental reasons, excessive soot in exhaust is minimized by limiting the aromatic content of fuels. ASTM D1319 is one of the most commonly used methods for determining the distribution of hydrocarbon types in fuels and other mixtures. Commonly known as the dye method, the sample to be analyzed is mixed with a fluorescent dye and applied to the top of a silica-packed column. The sample elutes through the column, which separates the hydrocarbons by type, including saturates, olefins, and aromatics. The differing affinity of the dye to bind with different hydrocarbon types yields distinct bands of colors within the column when viewed under blacklight. The distance traveled and the thicknesses of the bands of color correspond to the concentration of different hydrocarbon types within the sample. Recently, there have been urgent concerns regarding ASTM method D1319. On the whole, the method is somewhat dated and can take a significant amount of time to analyze a sample, often 75 minutes or more per sample. Additionally, the method relies on visual inspection of the color bands and the color changes, which induces some subjectivity and human error. More recently, the fluorescent dye used as an indicator was discontinued by the manufacturer. Due to industry outcry, a replacement dye was issued, but upon testing it was recognized that the new formulation simply does not perform the same as the old one. As a result, the most important reagent used in this method is, in effect, unavailable. A new prototype dye has recently been released and preliminary testing has been performed, but a definitive timeline for its widespread release and availability is unknown. As a result, laboratories, refiners, and processors are looking for alternative methods of quantifying hydrocarbon types in fuels. Two of the alternative methods for ASTM D1319 are ASTM D6379 and D6591, which are intended for the quantification of aromatics in aviation fuels and diesel fuels, respectively. Both methods use normal phase liquid chromatography with an amino phase column, along with refractive index detection. ASTM D6379, the aviation fuel method, can also be used with an amino and cyanophase two-column set for more optimal separations. Compared to D1319, the LC methods are more precise, more easily automated, and offer faster analysis times. Furthermore, neither of them require the use of special sole-sourced reagents that are or will be in limited supply. It should be noted here that these methods are only for quantification of aromatic hydrocarbons in these fuels and does not include the other components such as saturates or olefins. We'll start here with the LC configuration for D6379, which again quantifies aromatics in aviation fuels such as the commonly used Jet A. In this configuration, we use the LC plumbed with two columns, a 250 mm Shimpack amino column and a 150 mm Shimpack cyano column, both with 5 micron packing. We also plumbed a 6-port 2-position valve in line. The valve is not strictly necessary for D6379, but it is for D6591, which we'll get to later. But this enables the use of the same hardware for both methods. Additionally, the valve can be actuated for backflushing and column regeneration to maintain optimal instrument performance. An RID is used for detection, in which the analytes are detected based on changes in the refractive index of the eluent flowing through the detector. The first step in validating D6379 is having a look at the resolution of the peaks eluted from the column after injection of a system resolution standard, or SRS. The three peaks are non-aromatics, monoaromatics, and diaromatics, represented by cyclohexane, orthoxylene, and 1-methylnaphthalene. For this method, the resolution between cyclohexane and orthoxylene peaks must be 5 or greater. The results generated and shown in this chromatogram show that the resolution of this column configuration is 8.9, well above the limits for this method. We also tested an LC configured with a single Shimpack amino column, but with a 3-micron packing instead of 5-micron. In this configuration, the resolution was 7.1, still well above the specifications set in the ASTM method. So in terms of resolution, either configuration of the single column or the 2-column set will meet ASTM specifications. The next consideration is ensuring the linearity of calibration curves and repeatability of analyses. For both aromatic compounds, the correlation coefficients of the calibration curves generated with both the 2-column and single-column systems were 4 nines, and the y-intercepts were less than ± 0.01. Repeated injections yielded RSDs for peak area and retention time of 0.5 and 0.3% respectively. To test the LC on an actual sample, we acquired some Jet A fuel from the fuel farm at a local municipal airport. The sample was diluted 1:10 in heptane and run on the 2-column system for the data shown here. You can see good separations of aromatic components and no notable interference from the glycol-based fuel icing inhibitor that was blended into the fuel. We also ran the same sample on the single amino column system with 3-micron packing. We still get good separations that are in specification for the method. You can see the beginnings of separations on the monoaromatics due to the tighter packing of the column. Moving now to the instrument configured for ASTM D6591, which is intended to measure mono, di, and tri-plus aromatics in diesel fuels. You can see that the configuration of the instrument is largely the same as that for the aviation fuel method. For this method, we use the LC plumbed with a single column, a 250 mm Shimpack amino column with 3-micron packing. It is also plumbed with a 6-port, 2-position valve in line that is actuated after elution of the diaromatics to allow for backflushing of the tri-plus aromatics to the detector. Again, an RID is used in this system for detection. Like the jet fuel method, the first step in validating the D6591 diesel method is having a look at the resolution of the peaks eluted from the column, 4 in this case: non-aromatics, monoaromatics, diaromatics, and tri-plus aromatics. These are the 4 peaks we see here, represented by cyclohexane, orthoxylene, dibenzothiazine, and 9-methylanthracene. For this method, the resolution between the cyclohexane and orthoxylene peaks must be 5 or greater. The chromatogram shows the results from an injection of the System Resolution Standard, or SRS. The resolution using this system and column configuration is 8.9, again, well above the limits for the method. The backflush time, or the timing of the valve turn, is calculated based on the retention times of dibenzothiazine and 9-methylanthracene using an equation provided in the method. With the retention times here, the timing of the valve turn was calculated to be 9.24 minutes. This timing allows all of the diaromatics to elute prior to the valve turn, and then the tri-plus aromatics to elute as a narrow peak afterwards. Much like the jet fuel method, the linearity of calibration curves must be assessed for the diesel method. Here, we see the calibration curves for the 3 aromatic compounds have correlation coefficients of 5 nines, which exceeds the method specification of 3 nines. Similarly, the y-intercepts meet method specifications. Repeated injections show RSDs of 0.124% or less for retention time and 1.49% or less for peak area. Shown here are the results generated from using a sample of on-highway diesel prepared per method specifications at 1.0586 grams diluted to 10 milliliters. We can observe good separation of the three component peaks sufficient for quantification. Furthermore, we can see the beginnings of separations on the diaromatic hydrocarbons on the column. Even with these non-Gaussian peak shapes, the lab solution software enables easy quantification of these components. To assess the repeatability of this method, at least over the short term, we ran a series of replicate injections of prepared diesel sample. When we returned to the data system, interestingly, this was the chromatogram that we saw. We thought we had made a mistake and only done a single injection. However, when we offset the baselines of the 5 chromatograms here, you can see that there truly are 5 analyses. They were just repeated so similarly that the chromatogram traces overlap nearly perfectly. This repeatability honestly surprised us, as we were expecting to see minor variations in the data between the samples. As laboratories grapple with issues facing ASTM method D1319 and the unavailability of working dye, they need to find alternative methods for analysis until a replacement dye is available. ASTM D6379 and D6591 are acceptable and growing in usage for analysis of aromatics in jet and diesel fuels. The data we've presented here demonstrate the applicability of Shimadzu's HPLC systems and columns for these methods, and with the ability to provide the instrument and the columns, Shimadzu is a one-stop shop for these methods. Furthermore, a single HPLC can be appropriately equipped to handle both of these methods, precluding the need for multiple instruments if desired. Using LC-RID for these methods is faster, more precise, more easily automated, and does not suffer from the issues with reagent availability that plague ASTM D1319. With over 145 years of experience in analytical instrumentation, Shimadzu is a globally trusted brand for all of your analytical needs. Visit us at refineyourlab.com for more information on Shimadzu and our range of solutions for the energy and petrochemicals industries. Thank you for your attention to this webinar.